Okay, NP-hard problems. So just to explain, you're multiplying numbers together. That's a pretty easy thing to do. People know algorithms for doing that. You just, the simplest algorithms, you just take, if there are n digits in the number, you've got multiplying two n-digit numbers, takes about n squared time, you just combine digits. Actually, it turns out there are fancier algorithms we use in Wolfram language, for example, that can multiply numbers in n log n time or some such other thing. But basically, it's fast to do that. That's an easy problem. Now you say, what about the problem of taking a number and working out whether that number can be written as one number times another number, factoring the number? That's something which you could certainly figure that out by testing whether the number you have can be divided by 2, 3, 5, et cetera, et cetera, et cetera. It's easy to do it by checking lots of cases. The question is there a way to do it that is more efficient? So if you check all those cases, then if the number, you're going to spend exponentially more time than if you could do something just with the digits, because the number, that particular case, the number of digits in a number is roughly the log of the size of the number. And when you're doing all these divisions, it's something proportional to the actual size of the number, which is the exponential of the number of digits. Okay, that's just setting some context for people who don't know how these things are set up. So a big question is, can you solve a problem like factoring can you solve it efficiently? People kind of have, in fact, something invented right around here is the idea of public key cryptography that is based on the fact that it's easy to multiply numbers, it's hard to factor numbers. And an awful lot of the security of the internet and so on is based on the idea it's easy to multiply numbers, it's hard to factor numbers. And so the question is there something that will emerge in the future that will somehow discover a way to make it easy to, for example, factor numbers? And so there are different vectors to how that might happen. One vector is quantum computers. We can talk about that vector, then we can talk about the vector of solving that algorithmically. Quantum computers, I think people are very optimistic about this. I first started working on quantum computers back in 1981, and where my main conclusion was there were all kinds of problems with how you could make quantum computers work. Turns out those same problems are still with us today. But okay, so what's the point of a quantum computer? In a classical computer, in a classical mechanics in general, you say definite things are going to happen. You throw a ball, it goes in a definite trajectory. In quantum mechanics, sort of the big idea is there are many possible paths for what can happen, and all we get to be aware of is the probabilities for different outcomes. So many paths so in fact, in stuff we've done in the last few years, we've figured out a lot about how fundamental physics really works, and I think we have a much better idea of how quantum mechanics really works. And quantum mechanics is really a story of sort of many paths of history operating in the universe. So in a quantum computer, the point is that the idea is there are many paths of history. There are many computations being run in parallel. So when you're factoring that number, I said, oh, you have to try this number, this number, this number. Well, a quantum computer in principle could just try all the numbers simultaneously. So that's all great. All these threads of computation can happen simultaneously. The problem is the human at the end who wants to know what the answer was, they have to somehow knit all those threads of computation together again, and that's really hard. And in the traditional formalism of quantum mechanics from 100 years ago, what that says is just, and then you do a measurement, and that's kind of an atomic thing, and then you get an answer, and it will come out according to these probabilities. But in the standard theory of quantum mechanics, that act of measurement is not, you don't say how that happens. It's just a mathematical, atomic kind of thing. And turns out it's not so easy to do that measurement and knit together all those different threads of history. In fact, my guess is it is harder to knit together the threads of history than it would be to run the things sequentially one after another. But one doesn't know that yet. In fact, what's observed in quantum computers today is people say, oh, there are these decoherence times, there are these noise levels, we can't get rid of these things. It's, in practice, it doesn't quite work, but in principle, it's going to work. My guess is that that's wrong. And my guess is that it's the same thing people would say if you're making telescopes and you say, I've got this telescope, I have this theory of geometrical optics, I make a telescope, I can just make my telescope more and more and more perfect, and eventually I'll be able to see ants crawling around on the moon, if there were ants on the moon. But that's wrong. And the reason it's wrong is because there's a big piece of physics that you miss, which is the wave nature of light and the diffraction limit for telescopes. my guess is there's a similar problem with quantum computers, and that actually the data we now have about quantum computers and about decoherence times, all this kind of thing, is actually a great big clue to some pretty interesting physics. So that's one sort of possible vector by which people imagine that sort of NP hard, NP complete problems. The thing to say about these problems is, okay, the big fact about sort of computers in general is that there are universal computers. You can have a fixed piece of hardware that can run any sort of computation, any piece of software. So that's kind of the big idea from 1920, most famously from 1936 and Turing machines and so on. That is what lets us have software technology and all those kinds of things. There's another version of that, which is for these problems that are like factoring, which is kind of easy to check you got the right answer, but hard to figure out what the answer is. There is a set of problems which factoring doesn't happen to be known to be one of, but there are a set of problems which are so-called NP-complete in the sense that it's like a universal computer. Once you can do one of these problems, you can do all of them. So the typical problems are things like various kinds of graph coloring problems, satisfiability for Boolean expressions, all these kinds of things. Once you can do one of these problems, you can do all of them. It's kind of a universal computer idea, but within the class of these NP complete problems, non-deterministic polynomial time complete problems. Okay, so what can one do? Gosh, this is a much longer explanation than I thought it was going to be. But can one solve an NP complete problem with an AI? Answer, absolutely not. Totally the wrong kind of technology to use to do that. Can one have a problem which in general, there are many problems which in general are NP complete, but the particular cases of them that we care about turn out to be easy? And for that, yes, an AI can kind of memorize what things are easy and get sort of an intuition for what things are easy and be able to solve those things. I mean, one thing in Wolfram language, for example, there are endless mathematical computation things that we do where, in principle, the problem is NP complete. But in practice, all the cases that people care about are actually quite easy, and we can do them. And so that's a thing for which knowing where in the space of possible problems, where are the easy places, that's something for which I could imagine that is somewhat learnable by a neural net. In terms of the big picture, so the big question sort of algorithmically is P equal to NP. So P is the class of problems that can be done in polynomial time, as in if the problem size is n, then it's the time it takes to do the problem is some polynomial in n. NP is the class of problems where if you could guess the answer, you could check it in polynomial time, but you might have to spend an exponential amount of effort to figure out what the candidate solution is. So the big question's been around for a long time is P equal to NP? And that's a question that actually, gosh, this is a different topic, but actually we have some fairly interesting ideas about how that might work out. And gosh, this is going to lead me into a terrible rabbit hole. Maybe we shouldn't go there. Let me just say one thing, that there's a kind of geometrization of the class of computational problems that is something that's emerged from our physics project, where the fact that there's a geometry of a class of computational problems is related to the fact that there's geometry in space-time, and these things turn out to be closely related. And I think that there is a chance that we will actually get to prove something about P versus NP by looking at essentially there are a whole collection of things that are sort of related. There are things about black holes. Okay, so roughly a black hole, one feature of a black hole is normally, time ends basically in a black hole. Time stops. In the simplest kind of black hole, you can just, you're kind of going forward in time, and there's a singularity where time stops. And that's kind of like saying you're doing a mathematical proof, and your proof is always a finite length. Your proof always stops at some point. That turns out to be analogous to the situation in space-time where time stops in a black hole, and this is related to P and NP and so on. But this is not what I thought I was going to talk about here. So, yeah, please.
Back to more of like the getting it out there in the world and evoking people's imaginations. A lot of things that are coming out right now, like RAG-based applications, and
Yep.
just like kind of retrieval and putting data out there. You're talking about like multi-step things of like taking the AI and going through multiple steps, and it's not the greatest at that, but it can do those things. what are even some of the types of like AI applications that you think people should be like thinking about that are a little bit more expansive, that people are missing the mark on, that you think AI could do that people are not thinking about because it's a little bit too hard?
Well, I think the thing to understand, the general feature of machine learning, where's it going to work, where's it not going to work? It's a kind of an 80%, 90% type thing. If you've got a problem where 90% success is a win, that's a good start. Like if you're ranking search results, for example, and 90% of them are sensible, it's a win, even if 10% are totally crazy. If you've got a problem where you're trying to launch a rocket to the moon or something, and 10% wrong means you miss the moon, then it's a lose. So that's the first kind of deciding, determining thing. Now, I think in terms of what exists right now, the whole, the way to think about the LLMs, for example, is very much, I think, as a linguistic user interface. That is, there are things where we have in the past said we have to define the interface, but we're just able now to use something which is sort of a purely linguistic interface. What are use cases for that? I mean, there are a bunch of use cases which involve kind of human interaction. I think medical history taking is one example of one which somebody is going to do really well. I think it's going to work better with machines than it does with humans. I think it's a thing that's very complementary to what humans do. It's kind of, the machine can spend an hour trying to extract a medical history and ask a bunch of right questions and summarize that. I think the tutoring thing is really hard, but I think it is eventually going to work. It's something where there's 70 years of failures in kind of computer-based education of people trying to really have the machine. And one of the issues there is that part of the whole teaching story is it's a sales story, effectively, of can you sell the student on these ideas? And that's something that's not clear how that's going to work with the AI. So I think there are, well, what are some other places? I mean, name a field. Maybe I can.
Maybe beyond just like industry, I was even thinking about just like application, like multi-step versus even just like information retrieval and getting it out there. I mean, industries, I think there's a lot of like different industries you can go
Well,
to.
I mean, this question of what, under what circumstances should you just say, hey, I'm going to, abdicate in favor of my AI and let the AI do everything? I don't know. I think the problem with that is that a lot of what ends up being worth, at any given time in history, more things are getting automated. Before the things were automated, people had to do those things. Once they get automated, what happens? Well, people don't have to do that anymore. But then what's typically happens is you open up new opportunities, and then those opportunities are ones where there's sort of an arbitrary choice of should you do this or should you do that? You can start producing all kinds of new video types of entertainment. Well, you could randomly produce video entertainment and probably nobody will care. Rather, it's something where you've got to, there's going to be human choice involved in using this new tool of fancy new video generation, what can you as a human now choose to do that you can convince other humans is interesting and so on. So I think this kind of, as you open up more things, you build more powerful tools, there are more, that becomes something where the human is moving this sort of bigger lever, but there's still, you can't expect the AI to move that lever for you. Now, to some extent, you can say to the AI, analyze what the humans like and do what the humans like. And that's the story of, social media feeds and all this kind of thing. I think my feeling is that will be an unfortunate future for civilization, because in a sense, that's the thing eating, feeding itself back on itself. And this is reversion of the civilization reverts to the mean because civilization is eating its own kind of exhaust. And that's, that would be a bad thing. I mean, look, we see this happening in the machinery of the world in general. I mean, like, for example, not to complain too much about, things like academic peer review. Good example of something where, the system is built, because it's a very big system, it's built to kind of revert to the mean. So when if there's something new and innovative, the correct thing for academic peer review is say, no, we don't want that, because it's kind of reverting to this kind of, let's do what the collective wants, so to speak. And that's the same thing that the LLMs are effectively doing by ingesting, an LLM is very good at saying something like, what does the world typically, what what is the typical, best color for a tie for going to such and such a thing? LLM will do pretty well at an answer to that. There are use cases, for example, in my world of designing computational language. One of the things that I found LLMs useful for is, make up, what functions should we have? Because what functions do people typically, expect? Oh, there's something that's missing here. In fact, when the LLM writes code in Wolfram language, it will make up function names. And one of the things I realized at some point, other than just, okay, LLM, you should read the documentation and know that that doesn't exist, is if you keep on making up that function name, it's probably a sign that we should have that function, because it's something that, you've kind of, there's a few thoughts at least. I mean, I would say that offline use of LLMs is really quite interesting. People are often concentrating on online uses of things that happen in real time. But these things where you're doing data curation, for example, you're doing these things like coming up with function names, whatever else. For example, another big use case that we're seeing is you're trying to hook up some big sort of enterprise business system or something like this. You want to be able to do natural language queries. You want to do all these kinds of things. What you ultimately want is a connection to, for example, our computational language from the system, but the system is complicated. It has 10,000 pages of documentation. Nobody remembers how it works, et cetera, et cetera, et cetera. Well, then what you can do is kind of send in the LLM to try and read that documentation, figure out how to make this connection. You then look at the connection it made and you say, oh, that's not quite right, but it's roughly right. I can fix it. Then you get that connection, and then you can run it for the next 50 years or something as a piece of actual sort of solid code. So I think that's another use case that people are much more concentrating on, this kind of real-time use, and maybe not so much on this offline use where, just use the LLM once as a tool. Please. No, go ahead, I think.
So I'm starting my PhD here. I'm a new PhD student, and I'm interested at a macro level in accelerating like autonomous, intelligent, trustworthy robotics, so like embodied AI, essentially. What do you think the biggest gaps are in the, I want to throw this vector at you to just see what you would say, honestly, because I have
so when you
trustworthiness seems to be like one of the big things, like you just mentioned. Don't use ML.
Yeah, right. I mean, okay, so in robotics, for example, one of the things that does seem to be, very much on the cusp right now is whatever people, have different names for it, but it's basically using LLM-like technology to deal with action, behavior, whatever else. And I have to say, I think that, to me, that seems like a good use case, because it seems like, we manage, okay, another heuristic is, if humans can do it easily, there's a reasonable chance you can get neural nets to do it too. If humans find it really, really hard, like figuring out some computational problem, then don't expect the neural nets to be able to do it. But we humans do manage to, do manual kinds of things and, throw the water bottle from side to side and not drop it, maybe. And so I'm guessing that is a thing. I think what's non-trivial there is, for example, getting training data. Presumably watching videos is a good start. I've seen people just, have people who are just doing things in order to train a robot. And I don't know how much input data is going to be needed to successfully train that. I also don't know what the kind of interface between sort of solving the differential equations for the robot and training it in an AI way, what that's going to be. I mean, there's sort of an emerging class of neural net models that sort of have little differential equations inside that perhaps will be useful in kind of merging the differential equations for motion of things together with kind of the neural net story of what do we expect is going to happen. But I'm thinking that seems to me to be a thing that's going to work, basically. Now, the question then is, how do you tell the robot what to do? Because if you say, well, just imitate what I'm doing, okay, that can do that. But one thing that is an issue is, what is the language? What's the intermediate language that you might use to describe what should a robot do? And people have, I don't know, there's sort of choreography languages and things like this, but it's not obvious how you specify what the robot should do. And, for humans, it's like, well, you just tell the human, some verbal specification of what you want, and then the human kind of compiles that into actual motions. And maybe it's the same thing that will happen with robots. In terms of, how do you get the robot not to, do the wrong thing? This is a big trade-off, because any computational system that is really doing serious computation, you can't predict what it's going to do. If you could predict what it's going to do, there's no point in doing the computation. So you have this trade-off of you can make a system that is very, where you know exactly what it's going to do, and then it isn't doing very powerful computation, or you can make a system that's doing powerful computation, and then you have to live with the fact that sometimes it will do things you didn't expect it to do. And so that's an issue, and honestly, I think that's one of the sort of big coming societal issues is, do you let the computational systems, the AIs, do what AIs, do the computationally powerful things, or do you put big constraints on them, which...
Trust question I was asking, like how do you... That's where we're getting at, trust. Like how would you go about establishing that trust?
Well, it's a question of what you wanted to do. I mean, it's kind of like you say, okay, I want...
Spectrum, right? From like low, I want you to pick up this water bottle, it's very low risk. I want you to drive this rocket to Mars, right? A little bit more.
Right. I mean, but the problem is the general question of, I want the AIs to do the right things and not the wrong things. The next question is, what are the right things? What does that mean? And this quickly devolves. I mean, so, the first thing you say is, do what the humans do. And then everybody will say that's not the right thing. Humans do lots of the wrong things, et cetera, et cetera, et cetera. Then it becomes do what the humans aspire to do. And how do you know what that is? You go look at some book somewhere that says, humans should do this and that and the other. And some people will say this book is great, and other people will say this book is terrible. And, it's a mess. And there isn't, even the what are the possible things you might want the AI to be able to do or not to do, that's an issue. I think sort of making the AI constitution is really hard and is surprisingly little sensible work, it seems to me, has been done on this. I think it's one of the things that's sort of an interesting question. I mean, okay, political philosophy, big sort of developments in that 400 years ago or something now, at a time when sort of modern democracy was emerging, things like this. Now we have a different situation. There's a need for that to be rethought. What will come out of that? It's not clear. I mean, there are things you can play around with. I can give you some ideas that have all kinds of problems, but it's sort of interesting to think about. So one that's kind of fun is the notion of a promptocracy. So in other words, in a democracy, you might say you vote for this, that, and the other. There's a multiple choice thing you can vote for. In a promptocracy, everybody writes a prompt. You feed it all to a giant AI, and then it tries to decide what to do, okay? Is that a crazy idea? It's what could possibly go wrong, one might say. But it's interesting to think through, and to think through how that compares with kind of the standard way that the government works or something like this.
Regress to the mean again.
What's that?
You'd regress
Yes.
to the mean again.
Yeah. Well, that's a question of what. Right. Yes. But you see, you could ask people. Just like utilitarianism, has this question of, do you do something that 90% makes 90% of people happy, 10% really unhappy? You can kind of recursively ask people, what do you want to do with that? And so it becomes this kind of recursive thing. Like you could say to people, how much do you want to do unexpected things versus this? I don't think it works in the end, but it is interesting to think through. And I think it is one of these things where there fundamentally isn't a solution. It's one of these, there is no sort of mathematical thing that is the way that society should work. Yes, but then so another question which I was thinking about is this question of sort of the you have AIs, the AIs are very powerful, and an AI starts doing the wrong thing. What do you do? Well, you might think you can just switch the AI off, and but the AI is sufficiently powerful it might be hard to switch off, and also, it's not clear that you say, oh, the AI feels no pain, I can just switch it off, there's no ethical issue with doing that. If the AI is friends with 10,000 humans, that is not so obvious that you can switch the AI off without doing any harm. And similarly, if the AI is the repository of a huge amount of human knowledge, for example, it's not clear that that's an okay thing to do, to just sort of switch it off. So then you ask yourself, well, how do you think about this? And I think one thing I've sort of not really finished thinking through, but by the time you have a society of AIs, and you have, then you have not just the one powerful AI and then the poor little humans who can't switch it off, so to speak. At least then you have sort of this equilibrium of many sort of comparably powerful things. And then the question of whether, the bad AI, if the bad AI is excluded from AI society, it's the equivalent of, kill the AI, so to speak. And it doesn't matter what the internal view, whether the AI will feel pain when you switch it off or whatever. What matters is that it is sort of excluded from AI society, so it's not able to cause more trouble. And if you can imagine that there's sort of a development of something like the way that human society works in AI society, it's something that should be studied. People are starting to do that. You asked applications of LLMs. I mean, one of the scientific ones is thinking about LLMs as models of sort of human agents interacting with each other in the world and understanding kind of group dynamics of LLMs as models for humans. And so, this question of what would the AIs do if there's a whole sort of society of AIs, what will happen? Given that, and it's a slightly complicated thing because the AIs have been aligned with humans, and then then you're running these AIs and they're starting to sort of evolve in a way that's different from humans. Not clear what's going to happen, but I think that's a potential. It's a path to at least think about these things. And in the end, there are probably some ideas about political philosophy and so on that should come out of this, but I don't know what they are yet.
Steven,
Yeah.
what's your take on, like, are we discovering or are we building? You talk about computation is everywhere in the universe. I kind of want to know your take on, how much of this is discovery, how much is all these AIs actually we just discovering the concept of having so much computation?
Well, I think this question of what already exists in the world versus what do we invent, I think this is a complicated philosophical mess. Let's see, how to say something. I mean, we're going to end up talking about sort of the role of humans in the universe and so on. Maybe we should let's talk about a bit more about technology. It's a very interesting topic, but for another time. Please go ahead.
This time, my own question. So in the past, when I was maybe 8 or 9 years old, I tried to make different languages out of different sensory modalities like olfaction or taste. And I thought about the different ways that other organisms communicate with each other, either conspecifics or across different species. And I'm wondering, from your perspective of computation, if you've modeled different aspects of cognition in other organisms and the way in which they can communicate with each other.
Right. So the question of what, we describe the world the way we describe the world because we have the senses that we have. And, a lot of things about the way we describe the world are very fundamentally associated with the way we are as observers. So even I thought we were going to be talking about very practical technology here, but okay, let's even our notion of space is very specific to our particular characteristics. So for example, I look around in this room, and I think of it as being this room exists in space progressing through time. And that's partly because it takes less than a microsecond for light to get from the other end of the room to me. It takes my brain milliseconds to process what it's seen. So for me, it's kind of like one gulp of everything in this room in space successively happening through time. If my brain was 1,000,000 times faster, if it was like digital electronics, for example, really running in same kind of parallelism, I wouldn't think that there's space because the photons will be coming to me and I would already, every individual photon would have its own story, so to speak. So my perception of the world will be really different. And I think with other modalities of perception, the kind of the model of the world that you end up developing is fairly different. I mean, the way I tend to think about it is there's this whole concept of ruleal space, the space of possible rules that describe how the universe works, and kind of different minds are at different, just like people are at different places in physical space, so minds are at different places in ruleal space. And minds that are sort of well aligned are close by in ruleal space. It's easier to communicate between them. Minds that are more different, like different kind of educational background, whatever, or different species, they're further apart. We can do some communication with the cats and dogs about some basic, emotional kinds of things. By the time we get to other computational systems, like a favorite example is the weather, it's pretty far away in ruleal space. It's pretty hard. We can understand something about what's happening with the weather. We don't understand the purposes of the weather, the philosophy of the weather, things like this. It's far away in this ruleal space. And I think that's kind of at least my way of sort of at least parameterizing this question of what's, I've been very interested in this question about how do alien minds view the world? And I've tried to work out, so for example, here's an example of something you can do, is you look at a generative AI system and you say, I've got I've got this particular concept. I know where it is in embedding space. You take the generative AI system and you've trained it from human, input, and you ask it to produce something. Then you change the AI, so you modify its brain, and then you've got an alien brain that wasn't quite the one that was trained from human input, but is close enough that you may be able to recognize what's going on. You can, for example, you can do something simple like you just multiply the weights in the neural net by some constant. You quickly find the images that you get sort of blow the thing's mind. They get very bizarre. It's kind of interesting to see what happens. But you can kind of see how the thing becomes an alien mind, and we become less and less capable of understanding what those pictures actually are. And this is sort of a tiny proxy for understanding what an alien mind will do. But to me, it's a very interesting question. We have our first big example of alien minds in the LLMs and the AIs, and there's this question about, okay, well, how do we understand what's happening in that alien mind? How do we do science, neuroscience, I suppose, on the LLM? And it's surprisingly difficult. It's not obvious that, okay, one question is there a science of LLMs? Something I thought about a bit, and quite a bit actually. The tools we have are really good for studying that. And what can you say? I mean, in science, what we're typically trying to do is find a human narrative that describes something that we see in the natural world. So is there a human narrative that describes why the LLM does what it does? Why does, one-shot learning work? Why does, what can an LLM learn? Could an LLM, people ask, can it do math? Can it do this, that, and the other? How do we characterize that? Even when we're using a simple image identification system, we're distinguishing cats from dogs. What is that border between catness and dogless actually like? How do we characterize it? These things are very unknown. And we just don't have good scientific tools for thinking about these kinds of things. I've been trying to make some of these, but it's an area where it's not obvious whether just like it's not obvious in neuroscience, whether there's a theory of neuroscience that is intermediate between just neurons and whole brains. Please.
Speaking about the tools, the technology, you spoke about the Wolfram language as a tool, of course, upstairs, and you mentioned, and I think I'm quoting you verbatim here, that's why I wrote it down, that LLMs such as ChatGPT can only produce, quote, boilerplate code, right? I think that was what you said. And your point was that Mathematica has a finite set of functions, maybe some 7,000, that allow the user to get somewhere quite quickly. Yeah, I want to draw you into all those places where Mathematica doesn't have those boilerplate functions. For example, simple electronics or control theory. We probably both agree, maybe not, that you don't have those sorts of functions. And then coming back to what I think you said to this gentleman before, is it that the Wolfram language or Mathematica is somehow limited in boilerplate code, right? You have a finite set. Yet LLMs can write that much, much bigger set of boilerplate code, which is often very useful. And does that now limit the development potentially of the, shall we call it the Wolfram stack? Right.
So the question is, how big are the bricks you're going to build with?
Well,
right?
How many hammers can you have? Right.
What we've tried to do is to provide big bricks that allow you to build your tower more quickly. If the brick you have is a tiny piece of sand, it's going to take you a lot longer to build that tall tower. Now, if it turns out the brick we have isn't the brick you want, and you have to build it out of sand, that's a different story. And one of the things one can discuss is to what extent, what is the universe of ideas that are computationally relevant? That is, so let's take control theory as an example. We actually have pretty good control theory capabilities. It's not an area we've pushed terribly hard, but we happen to have developed a lot of stuff in control theory, although people don't know it very well. But electronics specifically, again, that's another interesting case where we have this thing called system modeler, which can represent things like electronics. It can't do, yes, it's a company we bought about a decade ago, which has been gradually integrated into Wolfram language. It can represent systems of differential equations and so on and it's used for systems engineering. It's used to make jet engine designs and study them and things like this. But you're absolutely right that there are things one can imagine inventing for which we don't have what's needed because you have to build it from sand. That the thing we're trying to do is to take the bricks that exist, that are bricks that have been developed, that people, there's no point. There's one thing one learns as a language designer. You may have some great idea, you think, about some piece of functionality that you say, it's really clever. I've got this great idea, I'm going to call it a quaggle or something. But the problem is, nobody knows what a quaggle is. So nobody can really use it. And so essentially in language design, what you're doing is this kind of art/science enterprise of saying, what do people actually understand? What do they know about? How can we encapsulate those things well to allow them to build based on the bricks that they understand? And so you're right, there will be, a lot of science I've done has to do with starting with sand and building new kinds of bricks, right? And if there are this question of whether, we have attempted, so for example, we're doing a project right now, I've been curious, a use for LLMs is you take all the libraries that exist out there for all languages, and you say, can we connect them to Wolfram language? Because we have connector tools. We have good encapsulation tools for all these different languages. They all have their own crazinesses, whether it's C or Java or Python or R or whatever else. They all, it's a horrible jungle out there. But we actually have now encapsulation technologies for all of them. So you can take any code written in those languages and encapsulate it and run it as something where you don't know that there's C code running or underneath there's Python code running or whatever else. And what we're providing is kind of the computational, language layer on top of that. So it's an interesting question. Can you go through and look at all the functions that have been written? And yes, we've done quite an analysis of this with some help from LLMs and other things of what's actually out there. There's a lot of very bad code out there, I will say. That's one thing that, but that gives one a sense of how far are we from, are there bricks that are worth having that we don't have? Gradually trying to build those things. I think it is as I say, there are some of the most innovative, interesting areas are ones where you have to build it from sand. But I think the goal is, my goal has been to sort of collect all the bricks we can from all the different areas where those things exist. And yes, there will be places where we've missed it and where a brick exists, but this encapsulation technology I'm mentioning, if anybody built that brick, we can use that brick.
Is that not, I don't mean to be rude, but is that not then getting to the place where you were talking about before, where the LLM already kind of provides that boilerplate code? Are you just saying that you're more confident in the structure of your brick in your...
No, the critical point is this. If you want to have kind of you want to have sort of a computational understanding of what's going on. You want to take, one of the big things, one of the things that makes it really easy for, if you're trying to encapsulate some random function from some random library somewhere, if you look at that library, a large fraction of the library is dealing with, how do you import and export images? How do you, transform from this thing to that thing? We don't need any of that stuff because we have a standardized representation of images. And so long as we have the glue, which we do, to go from that language's representation of images to ours, then we have something where once you take that piece, it then fits into this whole framework. And I hadn't really internalized how powerful that is until we started doing this. That you can have something where you've got something where the LLM would have to build. The LLM does not have this global view of what's going on. It doesn't have this kind of streamlined language for describing all these different pieces. So it has to build the glue itself. And by the way, in its 80% does it right, gets very messy very quickly because you have a few pieces of glue bridges and 10 glue bridges and one of them is broken and then the whole thing doesn't work.
But your bricks fit together. Actually, that's what
that's the point. Exactly. Right. I mean, that's what I just spent the last 40 years of my life trying to make happen. It's been a very interesting process. I mean, it is for me. It's great because I get to try to understand foundationally lots of different fields, like control theory, for example. It's one I don't understand very well, and I'm always frustrated when we're reviewing control theory functionality of Wolfram language because I don't really understand control theory that well, but this is forcing me to try and get there. But yes, I mean, that's the, it is a perhaps, it's an enterprise. This thing about integrating all these different computational areas, that's been what I just spent the last 40 years doing. I'm not sure, people don't understand that I think that's an important thing to do. But I think it's not as widely appreciated. People just say, oh, can I pull this random thing from this random library here? Well, maybe yes, maybe no, but it's not going to fit together with all these other things. And that's where the great power comes from, being able to combine these different paradigms in a smooth way. I see lots of hands here. Let me see, please.
I have a question on some other kind of bricks, which are tokens for LLMs, which like when you align them in time, it makes sentences. And during the Joshua discussion, you mentioned that it was not an efficient computation to do the autoregressive next token prediction. So what would be an efficient computation on these bricks?
Well, okay, so when it comes to human language, the number one thing that we learned from ChatGPT is human language is easier to construct than we thought. In other words, people knew that language had noun, verb, noun type structure. But I think what we learned, and in fact, I've been doing a big project related to this, is that there are sort of a higher level of construction that has to do with meaning as well as syntax that we can use for language. And so, for example, if you want to do language generation, I don't know yet because I haven't finished doing this, but we're trying to build kind of I'm calling it right now, symbolic discourse language, a kind of a way of representing, just like we have things like logic that represent certain kinds of valid arguments and so on. So you can say, and we have syntactic grammar that represent valid sentences. So the idea is to have kind of a symbolic representation of what possible valid sentences would be. So that's for the case of language generation, that's my guess. No. I mean, my meta approach to this, okay? So I'll tell you maybe an allegorical story which relates to this, okay? So when we were building Wolfram Alpha, 18 years ago now, Wolfram Alpha needs a model of, needs to understand lots of stuff about the world. Now, being sort of a foundational science kind of guy, the immediate thing that I might have done is to say, let's make a general ontological model of the world and use it to build the system, okay? We didn't do that. My approach was, let's build these individual pieces that work in these different areas, and then let's try to understand what their commonality is and link them together. That worked well. The same thing we're doing for the symbolic discourse language. So the idea is that there are these different areas that have little calculi. So for example, time has a little calculus, things that happen now and started then and so on. Space has a certain calculus. Human intentions have certain calculi of, you can't both want to do this and not want to do this. And, there's certain, and by the way, all of these things kind of crush out the poetry of the world, so to speak. They make definite things which otherwise might be sort of poetically uncertain. And I think, so that's so I mean, the current, these different calculi have somewhat different, right now, as we're building them, have somewhat different computational models associated with them. But I think you're asking, I mean, in this question about language is very much a sequential token by token kind of thing. And I think that's, how you actually construct it is a different story, but I think that's what it is. I mean, language doesn't need to be that way. I mean, we might meet the aliens who have some two-dimensional language or some graph-based language. I've been interested in graph-based languages forever. And the main thing that I always come up with is humans can't understand this stuff. Humans are very oriented towards this sequential kind of things, which, what's that?
You understand that?
No, okay, I'll tell you a funny story perhaps. Years ago, when I was working on my book, New Kind of Science, I had these complicated graphs, and it was before we had automated graph layout tools. And so I ran an ad for somebody to, human graph detanglers. And so like, who manages to be a good human graph detangler? And so like, we looked at lots of people, they said, can you detangle this graph? There's one young woman who was just spectacularly good at detangling graphs. And so I was like, okay, so she did a great job and detangled a bunch of graphs for me. And then years go by, and I look her up again, what's she doing? She's a leading knitwear designer. So it's kind of, I don't know which came first. I don't know whether the knitting came before the graph detangling, or whether the graph detangling led to the knitting. But so there are people, I think, that's my one data point, where who seem to be able to sort of, internalize how graphs work. I can't, even though I worked with graphs a lot. I mean, I can do something, but I can't, I wouldn't claim to have a sort of a global view of what's happening there. Please.
Yeah, I'm curious what you think if transformers are all you need, or especially when it comes to scientific discovery, and maybe you've talked about this already, but I'd love to hear more of your thoughts on whether or not transformers are all you need, or if there are other architectures that are needed to apply to scientific discovery.
I don't know what, I mean, I just tried doing some sort of different kinds of science with kind of reasonably leading edge transformer type techniques and other techniques. For the hard problems in science, they're surprisingly weak. So for example, when you try and do, solve differential equations, small numbers of differential equations, yeah, it kind of gets it roughly right, but it doesn't really right. It's, and if the thing runs for a while, it'll just get the wrong answer. Now, for example, for something like robotics, because there are many differential equations and you need sort of an approximate answer, it's probably a good use case for that. I mean, I was sort of transformers are, I don't know, I think one thing to understand about solving science problems is they're science problems where fundamentally it's a human imposition on the natural world, and another is it's what the natural world intrinsically does. In the what the natural world intrinsically does, kind of human neural net type architectures aren't really, they have no reason to be able to stand a chance because it's just not the way the system works. In things which are fundamentally, humans make that kind of distinction, can we make a neural net that makes that kind of distinction? The answer is it's probably going to work. And, are they, what are the right kinds of, what's the right architecture? Okay, so the main meta discovery of machine learning in the last probably 15 years has been that if you bash systems hard enough, they manage to learn. That wasn't obvious. When I played around with neural nets back in 1980, 1981, I tried to get neural nets to do things. I couldn't get them to do anything terribly interesting. And, but I didn't try nearly as hard as people try these days to get, and I'm sure had I tried that hard, I would have gotten even those neural nets to learn a bunch of things. So a big sort of meta discovery has been, you take this system, you bash it hard enough, it will learn. Does it matter that much what the system has inside it? Apparently not. Apparently it's a universal fact that if you have a system that has a certain amount of freedom and you bash it hard enough, it will learn. And so why does that happen? Why does it work that way? We don't really know. I've just been trying to explore this, actually. It's a very similar problem to why does biological evolution work? Why is it the case that we can successfully, by doing these little mutations, we can actually, solve the problems that are needed for evolution? And I think, in the end, I think, I have a guess, but I don't yet know. I was just working on this morning, actually, so this is very current stuff. I have a guess that it has to do with computational irreducibility and the fact that when you're in this high-dimensional space, that there is enough, essentially, intrinsic randomness in the behavior that you will always be able to find a way to not get trapped. So it's not obvious that you wouldn't get trapped. It could be the case that you're, in each local, you can walk around, but it's so sufficiently regular in there that you've gone around this loop, and you're just going to go around the loop again and again and again. But so, but I think it's a fundamental question. Why does machine learning work? Why does biological evolution work? My feeling is the architecture is ultimately not going to matter that much, and that you're going to be able to, if you bash almost anything hard enough, and it is high dimensional enough, and it has enough kind of computational irreducibility and so on, it's going to be able to learn. So, which thing you actually use will depend on what hardware you have and so on. And I was playing around actually with completely discrete neural net kinds of things that, currently, we can learn with neural nets that have these continuous weights and so on, and then maybe we can strip away some of the precision of those weights. But the question is, can you learn purely in a discrete system? I think the answer is yes. But you don't get to use derivatives in discrete systems. So you have to have a different approach than using gradient descent and calculus and so on. But I haven't figured that out completely yet. Please, I think.
So, question:
Yeah.
Do you think that the hallucinations or the tendency of LLMs to hallucinate can be made useful for purposes of hypothesis generation, of coming up with new ideas?
Yeah, I mean, sure. I mean, people use that a lot, I think, right now for, just come up with some crazy idea and it will come up. I haven't, myself, I've tried it many, many times. I haven't really found it super useful, but it's, maybe I'm a bad use case because I'm a person who spends their life coming up with ideas. So it's sort of something I do naturally, so to speak. And maybe for people who don't do that quite so much, it's more useful. But yes, I think, in terms of, look, one thing I think that is a potential sort of scientific use case is analogy making. So, to notice that this field over here that has all of this structure is directly analogous to this other field over here. That's something that humans find quite difficult because you have to know both fields pretty well to know their structure. But the LLM can kind of extract the kind of the shape of these different fields and potentially provide that analogy making. That would be my guess of the most powerful thing that one would see, that then the human has to be able to pick up and say, yes, that's actually interesting, as opposed to, the analogy between, circus performing and, I don't know, CEOing or something is, I don't know, I'm sure one can find an analogy between, I'm sure, I've tried, asking LLMs, find an analogy between this and that, and they come up with somewhat amusing, things to say. I don't think any of them have been that brilliant yet, but I would expect that's a place where you might be able to see something really quite interesting. In terms of this question about, let's say you're doing experimental science, you say, what experiment should I do? And it's like, well, there's this hole in the literature that's here. I can imagine LLMs being able to do that. There've been over history, there've been many attempts to sort of make formulae for discovery. So there was this one, a Soviet one called TRIZ, I think, which was a thing where it says, you look at the patent landscape and you say, where's there a place where there's a hole where this applies to that and, there isn't a thing here. Was not very successful. But I think that type of thing where you say, kind of, fill in what hasn't been done and so on, that's the thing that I can imagine LLMs would be useful for. Then, yeah, please.
You may have already addressed this. Given Elon and some of the other guys who predicted that AGI will be here within a year and a half or 2 years, what is your prediction? And then what do you think is the biggest obstacle or bottleneck?
That's what you mean by AGI. The problem is, in the time I've sort of been involved with AI-ish things, which is now, 45 years or something, the definition of what we mean by something being intelligent has moved many times. And typically what happens is the thing that people said, oh my gosh, when we can do that, we'll know we have succeeded. Then that's done, and people say, oh, that's just a piece of engineering. And in the end, the only thing which is, human-like is really a human. You can keep on saying, oh, but the AI doesn't have this, it doesn't have mortality, it doesn't have this, it doesn't have an endocrine system, it doesn't have whatever else it is. So I think it's sort of it's a moving target. I don't think that there's a well-defined sense in which, I think it's a messy concept. I think that, pick a criterion and you could say, when will we get to that criterion? One thing to realize about the evolution of machine learning, AI, and so on is, it's gone in these stages. And people, have had this sort of shock that ChatGPT worked. Everybody was surprised that ChatGPT worked. And people then extrapolate from that, a little bit like some of these neural nets do, and say, if it's gone to this point, it must be going, to the moon, so to speak, right? That's not the actual history. The actual history is, neural nets were originally invented in 1943, long time ago. Neural nets have progressively done certain kinds of things. And, 2011, machine vision kinds of things, mid-2010s, speech-to-text kinds of things, the surprise of language generation, video generation is not surprising at this point. There'll be things there'll be these different modalities but if you look over the last year, I don't think, I wonder what other people's impression is, but I don't think the LLMs got any better, really, at they got better at using tools, they got better in the tooling around them, but in terms of the raw, can you write a better essay? I don't think, other than for tool use and so on, I don't think it really got better. In fact, in some ways it got worse because people freaked out about the things that it was writing and said, let's put more and more constraints, and that made it harder and harder for the system to do the right thing. So my expectation is, you reach these sort of plateaus of capability, and I just don't think, I don't think there's a slope that takes one to the moon immediately. Please, yes.
My question is a little bit like, Brenda, thank you so much for coming. So I want to go back a little bit between the quantum computing and then the blockchain. There's some articles about it. What is your take that in the future, if you do some implementation about the quantum computing, will it break the blockchain? What's going to happen for those who have lots of investment in the crypto world? I just wanted to ask you.
Back about 7 years ago, I wrote this thing on April 1st of, I forget which year, 2016, 2017, something like that. I thought I would just write some little essay just for fun. It's called Buzzword Convergence, and it was called, I think, Quantum Neural Blockchain AI, or some combination of those words. And so I've been kind of waiting as the years go by for when will there start to be papers and so on that have all those buzzwords in together. And now there are. It turned out, though, that from a science point of view, there are actually some interesting analogies between blockchain and quantum and measurement and what it means to have a definite result in quantum measurement versus sort of knowing what the ledger said in blockchain and so on. I don't think, will some sort of moment happen when, the country X announces, they might announce it, but will country X actually have a quantum computer that can break all encryption? I don't think that's going to happen. That would be my, I think it's, right around the same time that warp drive is invented type thing. Maybe which by the way, is not as, now that we have, I think, a pretty deep understanding of how space-time works, I think I can say that the problem of inventing warp drive is not a science problem, it's an engineering problem. That we actually know in principle, if you think about gas molecules bouncing around in this room, gas molecules in actuality, go about a micron before they collide with another gas molecule and they get sort of randomized in their direction. But if you knew exactly which gas molecule to jump on, you would be able to go from one side of the room to the other at the speed of sound. Because these things are, you go this gas molecule, this one, this one, this one, this one, this one, but you can't solve the computational problem of figuring out which one to jump on. Turns out in space-time, you could in principle do the same thing. You can jump on the right kind of basically events in space-time, you would be able to go faster than the speed of light. The only problem is it wouldn't be the you that's doing that. It would be this thing down at the level of individual atoms of space that is nothing like kind of a kind of observer like we are. But in any case, I wouldn't worry about that. Maybe I'm wrong, but I wouldn't worry about that particular. I think there are many interesting questions about blockchain and its value and what it means for economics and so on. And I've been interested in kind of fundamental theories of economics and what they say about to what extent, you can think about, so when you think about space-time, for example, you think about all these little events that happen that change this network that we think is the structure of space. And when you think about an economic system, you think about all these little transactions that happen, and then somehow those transactions knit together to make this economic system that has notions like price and so on. And so I've been interested in kind of how you go from, whether there are foundational theories of economics that are somewhat similar to foundational theories of physics. I don't know the answer yet. Please, let's see, yes.
I guess my question, relating to back when you said, if you bash a computer hard enough, eventually it'll learn how to predict correctly, then wouldn't you say just having the different LLM going against each other and just letting them go battle royale and having the hallucination cancel out each other will eventually fall into like Gaussian distribution, making it predicting what it is, or
well, I mean, this mixture of experts thing is a kind of some version of that. But I think that if the question of whether sort of the LLMs left to their own devices will eventually, what will the society of LLMs look like? I don't know the answer. I mean, is there a central limit theorem for society, so to speak? We don't know the answer to that. Or is it the case that, is there instability? If you put a lot of humans together, what we seem to observationally find out is that most of the time kind of is equilibrium. Occasionally it spurts out and something crazy happens. But most of the time, and so maybe it's the same way with LLMs, but we don't know. And I mean, we can imagine kind of a mathematical theory in principle of kind of what is the continuum limit of a large society of LLMs. You've got all these LLMs interacting with each other, what will they do? I mean, that's similar to what people want to do in economics. If you're studying, if you're studying a market, for example, you have a lot of traders doing different kinds of things. What will be the aggregate effect of all these traders in this market and so on? And there's a lot that is not known and not figured out about that, please.
Just on her question again. So, but isn't the fight of LLMs or the equilibrium depends on the value system that each LLM has? Because when the humans are living together, I mean, they have a value system that I have to survive or I have to. But if the LLMs may not have a value system or have a value system, that will determine how they live.
I wonder. Because it could be the case that, let's say the LLM has a crazy value system. It starts with a crazy value system. And then the whole thing, it could be that the very dynamics of the interaction between these things causes them to necessarily end up with a value system. Because with humans, if the value system was, I'm just going to kill all other humans or something, then pretty soon the humans go extinct. And so that, that value system is kind of selected against. So in a sense, maybe we don't know. I mean, maybe there is some sense in which anything that, if we predicate the thing on the fact that it survived, that the system survived for a certain amount of time, maybe there is some necessary features of the emergent value system. But I agree that it's not obvious what happens. And at the beginning, you started off, and you can see this. I've studied these little cellular automaton systems a lot, where you have these local rules about what these different cells do when they interact with their neighbors. And you can easily see cases where, depending on those interactions, things either they form sort of big blobs, they all die out. Lots of different things happen depending on those local interactions. It depends on the local interactions what the outcome is. So I don't know whether good question. Yeah, please.
One quick question.
Yes.
On the topic of cellular automata, I'm wondering if you've looked into Michael Levin's research on bioelectricity and unconventional forms of intelligence. I think that's...
Someone was just telling me about this just about 2 hours ago. So the answer is not as much as I should. And I think the thing to understand in things I've tried to do is that, intelligence is, I think, there's computation, there's human-like intelligence. Computation is pretty ubiquitous to lots of systems in the natural world and in the sort of constructed world. I mean, it's easy to make a computationally sophisticated system. Whether that computationally sophisticated system is aligned with us humans, it's like the weather has a mind of its own, but its mind is very different from our mind. So, the fact that in our bodies, for example, the immune system is doing all kinds of complicated computation. Potentially, it's hard to compare how its sort of molecular scale computation compares to brains. You could ask, can you have a philosophical discussion with your immune system? Well, it's not very aligned with human, with those kinds of human types of descriptions and so on. But so I think, there's much to do in sort of, unconventional computation is, right now, we have two examples. We have brains and we have, digital electronics. There are clearly many other forms of computation. For example, the obvious ones are molecular scale computations of various kinds. And there's, that's a thing that's surely coming. I mean, the big difference between when people talk about nanotechnology and so on, the big difference in electronics and nanotechnology, I think, in the end, is in electronics, you're merely transporting electrons around. In what you want to do in nanotechnology, you're also transporting other kinds of atoms around. And I'm sort of surprised that people haven't done more on kind of the analog of electronics for transporting atoms, because it isn't fundamentally that hard. And the reason that, the reason one might care is because we humans, biological humans, are sort of molecular scale, atomic transporting kinds of systems. And if we want to interface to us, it is useful. We're a great example of molecular computing. We can build engineered molecular computers, and that's a good thing for interfacing to us. So, but I should learn more about this. Please.
Sorry, it's an honor. Thank you for coming. You have spent a lot of time collecting data on yourself. Can you talk a bit about the habits and systems that you use and what you would recommend to someone like wanting to start this off, but with the technology acquired?
Well, okay, so yes, I started like 30-something years ago collecting whatever data I could because it was easy to do. And all the email, 3 million emails, well, no, it's 4 million now. Every keystroke, heartbeat, all sorts of other things. It's a pain to keep all those systems running. I mean, that's one thing to understand. I mean, I realized, why haven't more people done this? Well, part of the reason is, I run a company, I have sysadmins who work with me, things like this. These systems are always breaking. It's always like, I have something. I mean, one thing I do is I have things that summarize every day. I summarize how many keystrokes I typed, how many steps I walked, how many whatever else. And if I don't see that email, I know something went wrong. And I have another thing every week, every month that tries to give me summaries of things. And things break. And that's one feature of. But I would say that the single most useful thing for me, I mean, I'm an email-based dinosaur, so to speak. I'm not really it's more of a nuisance, actually, when you're doing texting and so on. Archiving the text is kind of a pain. And by the time you've got all these different sort of channels, it becomes kind of painful to do it. But the thing for me, the single most useful thing is kind of enhanced memory from knowing all this stuff about what happened in the past. And I think I have a reasonably good human memory, and that has spoiled me in terms of now I expect much more. And it's like, I run into some person, they've got a name, except here we don't have name tags, which is bad. And then I can, like when I get a piece of email from somebody, okay, sort of internal fact, when I get a piece of email from the outside world, another piece of email comes in a few seconds later, which is the result of searching from the person's name and various other things in the email that came in, searching my archives, so that I immediately know, I corresponded with this person before, 20 years ago. And that's very helpful to me. I mean, it's, it improves my life, so to speak, and it improves my ability to sort of interact in a sensible way with people. And that's something I'm trying to do right now is to get a good vector database type system for not only being able to do purely, literal searches, but, one of the things that I have to say, I'm a person who writes a lot. And so one of the things that's a terrible moment is when I realize I'm writing something and I'm like, I'm sure I've written about this before, but I can't remember where exactly. And can I at least put a link in? And it's like, what I want to do is to have something where I have a real-time kind of LLM vector database thing that's in real time pointing me to stuff I've done before that's related to what I'm doing now. Those are a few things. I mean, another thing that's worth doing if you're young, which you look like you are, is, for example, with medical data, okay? Just collect it, because people will tell you, you shouldn't measure this thing because, if you measure that and you have a false positive, you might be going and, taking yourself apart to figure out whether this or that is true. But if, like I measure lots of random things about myself and people will tell me, you have this thing that's out of the normal range. It's like, okay, well, I'm not worried because it's been exactly the same value for 35 years. So I think I'm okay. No, I don't. Yes, I have considered it, but I just poking into me is if there was a Raman spectroscopy-based CGM, then I would be an immediate customer. But the PPG I'll do, but the In any case, I should. But anyway, this is one. If this thing about people often don't recognize the value of these time series, and I think that's a useful thing. It's certainly been useful for me. And there are occasional things where you say, given that you have a lot of data on yourself, there are occasional questions you ask where you're like, I'm trying to understand some trend about myself. I've noticed this or that thing. Like I've noticed, like I have all these trends about email. I'm an email dinosaur, as I said. My main way of interacting with the world is through email because it's a systematic thing where I get a few hundred emails every day and I know how long it takes me to grind those down. And I have all these plots of the email, pending email and so on. It's very satisfying, actually. If you've got 5,000 pending emails and then you spend a day just grinding the thing down, you can see the thing going down and so on. It's very, very satisfying, even though it's going to go back up again. Another thing I might mention is when you get feedback every day for things like how many keystrokes you typed. I find that fairly useful. I can't really say exactly why, but like yesterday, I think I had a 55,000 keystroke day, okay, which is pretty decent, and it means I was fairly productive. It has it's useful to me to get some sense of if I'm doing this kind of thing, then I'm more productive than if I'm doing that kind of thing. A few thoughts? Yeah, please.
First off, I also track a bunch of stuff about myself, and it's really useful and interesting to see sort of the trends and everything. But I'm a founder and a developer, and I feel like this is the golden age of AI right now because it makes me much more efficient as a developer. But still, all the experience I have, that makes me able to see the mistakes it makes, and so when it gives me something that's a problem, and that means that I have an edge basically on other people who are not developers. But basically, I think the sort of the trend that everybody's expecting is that in a few years, 5 years maybe, that the average person will be able to get the same output as me, and sort of my experience as a developer doesn't really matter anymore. And it seems that everyone is planning for that world in which AI is taking over jobs and everything is getting better. And my question for you is that earlier you said about you go through these plateaus, and I'm wondering if you think that there could be either a hard plateau or maybe even a ceiling that we reach in which just the existing LLMs, maybe it's because of the frameworks they're built on, are just going to hallucinate more, and they just become much more inefficient.
Yeah, I mean, look, I think you see a certain kind of functionality right now for linguistic interfaces with LLMs and so on, code writing with LLMs. That will get tweaked. It will get gradually better. I mean, look at what's happened with machine vision and image identification. There was a big jump in 2011, 2012, and then it's gradually gotten a little better, but it's not like it's jumped dramatically. There was the big jump and then gradual improvement. I think the big improvements now will be better harnesses, better tooling around the LLMs. The LLM does some powerful things, but put tooling around it to make it really useful. With respect to the whole, will developers be useless type thing, I have to say, having spent the last 40 years trying to automate sort of how computations get done, when I see people saying, my gosh, it's amazing, you can get the LLM to write this or that thing, it's like, look, that's one function in our language. You've been able to do that instantly for the last 30 years. And it's like the fact you didn't know that and you insisted on writing kind of low-level code to do this is like, the reason that happens, I think, is that software engineering is the act, it's all about writing that low-level code. It's not about kind of thinking, what do I really want to do computationally? That's considered to be hard. People say, oh my gosh, it's so difficult to use your language not because it's hard to make, it's very easy. It's kind of cheatingly easy to make stuff actually work. What's hard is to figure out what you want to have work. And people kind of then like, oh my gosh, I've actually got to think type thing. But in terms of do I expect, look, I mean, the history of kind of, what people have done with themselves and whether, experience is useful, all those kinds of things. I mean, I did this study a while ago of just jobs in the US since 1850. Okay, you can see, it used to be the case, the pie chart, big piece was agriculture. That got crushed down to almost nothing. And the fundamental thing that happens is when one area gets automated, there's an area where lots of people do it, you automate that area, then that automation allows many new possible directions to open up. And then people explore those new directions, and as economies get more developed, it seems you get more fragmented. There are more different categories of jobs. And I would expect that the same thing will happen. That is that what gets automated now becomes kind of zero, low cost, and then more things are possible. Now, my feeling is, if you're planning for how do I succeed in that economy, my feeling is that knowing about more kinds of things and having judgment and experience about more kinds of things is the most valuable thing. Because any specialized area can be automated. Knowing sort of the big picture is, by definition, it's kind of like you're going to have to make a choice based on this big picture, and it's not something that the AI is not going to tell you what to do, because there are an infinite number of possibilities, and it's up to you to decide what to do. So I do tend to think that the sort of the value of incredibly specialized education is probably going to go down. The value of more general learn to think type education is going to go up. And I'm kind of hopeful that for people who sort of have a strategy, spend some part of their time figuring out the strategy of what to do, that will always be a useful skill. Because by definition, the AIs don't know what they should be doing, because that's not what they're, there's no intrinsic strategy for the AIs. A few thoughts. Oh my gosh, more questions. All right. Okay, great. Please.
You spoke a little bit about neuroscience earlier, and how there's a lot of things going on in the neuroscience world right now, where you have the implant and you can, and with the help of LLM, you can detect which part of the brain is getting triggered. This might be a huge jump, but do you think at some point there is a chance that the LLM can detect different kinds of skills and what part of the brain it triggers, and there is a way to, if you want to learn a skill and it can trigger these things and you can learn these skills automatically, is there?
Right, well then the question is, what do you need your brain for at that point? And so, no, I mean, this question about what do neural user interfaces look like is an interesting question. I mean, because, we have learnt how to use graphical user interfaces, things like that. We all have kind of common experience of the graphical world. What's happening inside brains may be more different than that. And whether the LLM can learn for each of our individual brains what the right way to talk to us, so to speak, at a neural level is, probably there's some things that can be done there. I have to say, I think it's an interesting question. What will it feel like if you can have, if you think something, I mean, right now, you think I'm going to move my hand and the hand moves and something moves with it and so on. If you think something and then that thought is picked up by, some AI, LLM type thing, that thought is then developed in your brain and fed back to you, what is that going to be like? And at what point in this kind of ship of Theseus, like philosophy type thing, do you realize, oh my gosh, there's no brain left. It's all, I have this, you start off with the brain, you start replacing pieces of it with the LLM, and then pretty soon, it's kind of, there's no, so I don't know what that's going to be like. I think I think, okay. Yeah, right.
I also love it.
Yeah, right. I mean, it's
Second.
Learn how to fly a helicopter. Right, download it.
Right, I think this question about whether you're going to be able to, okay, one thing about, brain-to-brain transfer of knowledge. Okay, I think I'm not optimistic about that. It's like if you take a computer and you say, I've got a running computer and I'm going to transfer all this information from the one running computer to another, it's not going to work because the way it's laid out, its memory and so on, it's all different. The way that humans transfer knowledge one to the other is they package up all those neural, impulses into words and language. Language is the transport layer. Then the brain at the other end unpacks that language and turns it into their internal, capabilities. So it's an interesting question whether if you had sort of two people with neural implants, so to speak, can they develop a private language that can transfer thoughts from one to the other without going through something that is like our ordinary language. My guess is that it will end up being somewhat like our ordinary language. That won't, but I don't know for sure. All right, last, I think we got 3 last. Okay, let's see if I can do this quickly. I don't know if I can. But
Silly one. If teenagers get this addiction to TikTok, I feel like LLMs or AI is the TikTok for smart people. And I feel like it becomes this crutch that you potentially get a decline because you don't actually experience the pain it takes to read the entire article.
People say this about, technology I built. People say, oh, when all the kids just do their calculus homeworks, with technology, they won't learn anything. I think completely the opposite is true. So in other words, the thing is, if you grind through all those details yourself, you only get to do it a few times. If you can just, jump over all those details and get the big picture of what's going on, that's a thing that's a much more useful human thing to do. So I don't think that the lack of having to follow the details is, I think that just sort of enhances what we humans can do rather than kind of dumbing down what, now, it is the case. If it gets to the point where the typical paper you read or something was written by an LLM, there's a model of the world where, okay, one thing that's perfectly real is somebody says, I've got 5 things I want to say, but I've got to write this report. I can't just list those 5 things, I've got to write a report. So they take the 5 things, they feed it to an LLM, the LLM produces a big report, they send the report in, people at the other end take that report, they grind it down with an LLM to get to the 2 things that they care about. But this isn't completely crazy. This is because then you're using human language as a transport layer to go from one sort of alignment of questions to another alignment of questions, and that's not crazy. That's a reasonable thing to do, because otherwise you'd have to build a system that that glues those things together. So anyway, speed, yeah.
Do you think it might be possible to model and predict human cognitive state relative to an automated system? So this is a big issue on something like a pilot of an automated flight deck. It's the cause of most of the current accidents, where the cognitive state of the human operator is different than sort of the embedded cognitive state that the automated system is predicting. When that divergence occurs, usually the airplane gets into trouble. And this would apply to other complex systems.
No, it's interesting. It's similar to the tutoring problem. Can the AI kind of understand enough about what's going on in the student's brain to be able to say why they're confused? One thing that I think really helps in the tutoring case is, with LLMs, for the first time, we can not just look at the answer, but at the thought process that was gone through. So I would imagine in the flight deck example, I could imagine that if the LLM is watching not just what button did the pilot push, but is also looking at, hey, what are their facial expressions? I can imagine that there's actually quite a bit of mileage that could be got there by seeing whether those are what you would expect based on, the stall warning horn just went off. What are the facial expressions? Are they what you would expect, or are they something completely different than you would expect? It sounds like a good use case, actually. It sounds like something where, being able to observe the humans better, model the humans, see whether that's what you would expect based on what the system thinks is going on. Good idea, actually. So you should do it. Maybe you are doing it. Please, last one.
So to close out, I'm going to be a bad actor and selfishly co-opt your captive audience here. Blue Yard Capital invested in a company called Chemify, led by a University of Glasgow professor, Lee Cronin. He is building a chemical synthesis language. You have the human computational language. He has assembly theory. You have the theory of everything. We're going to have a dinner in September. I would love to have you and Lee Cronin on a panel together.
Lee, I was at a conference with Lee actually recently. He came up to me and just insulted me. And then he apologized later and sent me an email apologizing. So I have a rather strange relationship with him.
Well, we'd love to hear you talk.
But to say something about automated labs, actually, I've been involved for a decade or so with a company called Emerald Cloud Lab that's been building In fact, I just visited them in Austin. They have a new facility in Austin, Texas that's 10 times bigger than their previous one. And what they've done is take kind of all the standard biology and chemistry experiments, about 200 of them, and tried to make them be able to be automated using Wolfram language as sort of the interface. And it's rather a lovely and impressive thing that not enough people know about yet. That, I mean, it's been a lot of work to take all these instruments that were never really intended to be operated by computer. They were intended for somebody to push the buttons on the front panel. And so, the Emerald guys eventually have little robots that push those buttons, but all under sort of API control. I have to say that I've been wanting to do my first biology chemistry experiment in my life, I suppose, on this Emerald system. But I was about to do this about 6 months ago, and I'm like opening it up, and it's got all this lovely documentation. It's all Wolfram language stuff, and I'm like, okay, how do I generate random proteins and measure affinities and things like this? And I look at one of these instruments, and it's got like 50 options for the temperature of this and the this and the this and this, and it's like I have no idea what to do with this, because the guys who run that company were saying, look, our users are people who have biology and chemistry PhDs, and each one of them learnt in their lab, oh, you should use 317 degrees as the temperature for this thing. So actually, I've now gotten these guys to use kind of AI to be able to basically say, what are it's a good use case actually for LLMs. What are the typical ways that these parameters are set based on a million papers that people have written, the method sections for those papers and so on? What are the typical things that happen? Also, from looking at actual experiments that have been done, what are the typical outputs that you get? So this is, I think, the Emerald guys have kind of the most serious effort at trying to make an automated lab. And it is, by the way, if you're into kind of pharma, business, chemistry, whatever, this is definitively the future. I mean, it's really quite an impressive thing to, relative to a typical, the graduate student who learned 5 or 6 different instruments, and now you've got 200 different things that you can use, hopefully soon, without having to know so much in detail about them. It really dramatically opens up what's possible, and I think it really changes dramatically the economics of doing a startup in the biotech area, et cetera, et cetera, et cetera. So lots of interesting things to say. I think I have to say it's funny because I think I was at an event, what was it, only 2 weeks ago now, where you mentioned, it was a funny thing because Lee comes up to me and says, if you think the universe is computational, what kind of computer is it running on? I'm saying, Lee, that just doesn't make sense as a question. It just doesn't make sense.
Well, we would love to have you test that out together. It's very much like an experimental system. You have all these parameters, you got to keep them appropriately tuned.
Yes, right. But anyway, the thing I have to say to finish that thought, because it was just a funny human thing. I was at some other event, and a person I know, actually, a very MIT person, who was comes up to me and said, "That person over there just insulted me." And I'm saying, "Who?" And he points at, "It's this same guy." I said, "Well, you shouldn't feel special because he did that to me yesterday." So anyway.
He's just from Glasgow. That's what I do over there.
Stephen, thank you so much. You've been very, very generous with your time.